Yeah. So we should be recording now. All right, so last time we stopped on that project. It's project number 19, child and passenger active safety in vehicles. So as I mentioned, when you are talking about the motivation part, make sure you try to include some statistics from references. And then the objective we have here is to improve child and passenger safety using safety seat and safety belt tracking system with cameras and sensors. So one idea is to make sure that you can see without the driver looking in the back seat, can actually see what the child is doing, or learn about what the child is doing, maybe from the vehicle, if you have a smart vehicle. So there are different ways of looking at this project. One of it is basically in machine learning, you can know the age of the person. There are older machine learning techniques where you can actually find the distance between the eyes and the eye and nose and the eye and lip and so on. And these ratios can give you some information about the age of the person. Now, given the deep learning and the available online training, you actually can have more uh, um, well-trained, ready to use the deep learning algorithms that you can also start with. Um, so this project is basically part of artificial intelligent machine learning and image and video processing, where you need to check if there is an adequate distance between the neck and the build of the child. Also, you can have sensors that can detect that the child is buckled up. Now, there was actually an incident before that also in the news that it's not it happens that sometimes parents forget their child in the vehicle, and if the weather is too hot, then they actually can die in that vehicle. Sometimes they leave pets and stuff like that. So if you have a type of intelligent systems that can connect your vehicle with your phone and can tell you about a situation like this, can actually be a life-saving for some kids. So these are all type of projects that you can work on. It's all related to the safety of the children and passengers and drivers, either if it's actively driving or even if it's parking. So this is also one project. Last project I have here is basically low complexity orchestrated reconnaissance. So this is looking into having limited resources. If we have limited resources and we want to do some reconnaissance, so it's basically a military application. We have a limited number of satellites, we have a limited number of UAVs, and we have limited number of radars. How can you utilize the available resources with a low complexity allocation method to be able to track the targets that are of interest or the hostile targets? So the goal is the cooperation between radar and communication system in a way with a high level strategies that can actually minimize the computation. So one technique I looked into here is a fuzzy system. So is any of you familiar with fuzzy systems? No. Okay, so fuzzy system is basically it was very common system in the 90s, early 2000s, basically used to design control systems without getting into the depth of mathematical derivations. And it's basically the main idea is to try to think of how a person would actually quickly give a decision about a specific, given a specific inputs. So let's say we look into that map that we have. The map consists of these areas. There is a urban area. Then there are some flying. These are all things that you can see on the map. Flying object. You know there is a radar here. This is your radar. You know you have a ship with a radar here. You have a radar here, and you have all these flying objects and moving objects. Now these objects might be an object that you are familiar with, so you know that is it's a non-hostile. For example, it's a commercial ship, and it's far away from your other ships or ships or from your radar or your shore. But you can have a target, you can have another type of vehicle moving that is unknown. You don't know if this is a hostile or it's non-hostile, and its distance is medium. And then you look into this, you find it's hostile, but the distance is medium. You find this hostile, but it is far. This is unknown, but it is far. This is non-hostile, but it's medium. So if you have all this information, and as a human, if you look into it, you can make a quick decision based on the distance and also the status of the vehicle, if this should be a vehicle of interest to track. So basically, it's going to be based on the status, and it's going to be based on the distance. You can just quickly give you don't have to have an exact distance of that moving target. Again, by the naked eye, you can just say, okay, maybe this one we should first focus on this one before anything else, because it's close by. So that is what we're trying to mimic on the fuzzy system. We're trying to build a system that can actually take a quick decision without doing a lot of exact or accurate computation. And this case is called the fuzzification step, where you divide that system into these type of fuzzy rules or fuzzy inputs: far, near, medium, far, close by, these kind of things. And then based on that, you define some rules. If it is nearby and it is hostile, for example, try to engage or try to track. And then after that, you get out an output, which is what is the decision you're gonna do. These are the three stages of the fuzzy system. So in that scenario, where you're trying to do some reconnaissance, you can actually have that type of system. You have a target, you have some sensors like satellite, UAVs, and radar. And then these are gonna track the target. Input that you have is gonna be in the fuzzy system, which is give priority. Who is the target that is more important? So you should focus your resources, which is limited to that target. And then based on that, you send a high-level commander strategy to take a decision if they should engage or not with that target. So it's basically a way of resource allocation with limited resources. And given there is different types of resources, some of them is radar, some of them are taking images like UAVs, satellites are taking images. Some of them can engage like shipborne radar. Some of them can also like UAVs, like a drone, these kind of things. So if you have these resources, how to build a system that can do quick decision with low complexity, and at the same time be sufficient for what your mission is. It doesn't have to be very accurate, mathematically driven optimization problem, but it can actually it can still do the job with even lower computation. All right, so this is my last project for the project's ideas. Of course, a project of your own creation will actually be more recommended. You just need to provide a good justification. Again, good one-pager and one good quad short. Now, I did update my the details and instructions for the submissions, so it's clear for everybody what needs to be done. So as I mentioned before, it's going to be one student per project, and these are actually the points for each part of the project. And I have uploaded these on Blackboard, so you'll find assignments already ready for you to submit, and each one of them has these points. So the thing is, the course project is going to be 40%. So I give all the assignments 40 points. The first one is a project proposal on the one pager is 3 points. The quad chart is 5 points. The progress report is 7 points. The final presentation is 10 points, and the final report is 15 points. So as you can see, as you go from the first assignment to the last assignment, you have more points. So this is how it's going to be divided. So basically, which means that the project proposal is 3% of the whole course project, grade. And the final report is 15% of the whole course grade, because if you sum up all these points, it's 40, and you have 40% for that for the project. Now these are the deadlines. They are the same. I just added a bullet here that shows the presentation in the class versus the submission of the presentation. So we are going to present on the week of May 4th for the final presentation, but you are going to submit it on the May 11th. So this is just two different dates. Same thing for the quad chart, submission is on a day and presentation is on a different day. So this is just updated. It's also uploaded to Blackboard. I also last time I showed you what is the outline of the proposal. As I mentioned, proposal is preferred to be in LaTeX, but if you can do it also in MS Word. And this is the setup. This is one page, and this is what I expect to be inside the page. So you have you put the title, you put the author, and then you have 3 paragraphs. One is a why, what, and how. Okay. Quad chart already talked about it. You need a figure to show the quad chart. Now the progress report, it has to be in IEEE double column layout, which is one I'm going to share with you today. I already have LaTeX sample that I'm going to upload to Blackboard. When I'm also going to show it how it looks like today. This cannot be in MS Word, so you're going to lose some points if you submit it in MS Word. So I want you to submit it in LaTeX. You have enough time to do the progress report. Progress report needs to have the title, the authors, and their affiliations. Of course, in this case, there is only one author. And then the literature survey, the problem statement, and the references. And I also added the layout of the progress report. I expect you to submit 3 pages. So you also get an idea how many pages you need to submit. So here is the layout. This is going to be double column. So you have title, author, and affiliation. Affiliation here is the UND. And then you add the introduction, which is a section, and then related work, another section. Then you have the system model with a figure, and then you have the references. This is sufficient for the progress report. If you want to add more, it's okay, but this is enough. Now for the final report, also needs to be IEEE format, double column, and not be in MS Word, and all these things needs to be in it. Title, author, abstract, introduction, problem statement, analysis, results, conclusion, and references. And here is also how it's gonna look like. So this is expected to be between 6 and 10 pages. So try to not be less than 6 pages, don't go over 10 pages. And it's going to have the title, author, and affiliation. Then you add an abstract here. So you can see the difference between the progress report and the final report. You need to add an abstract to your introduction. Then you also have analysis added. You have results, which, of course, if you have results, you have some plots. So you need to show, you can have some tables. Conclusion and then references. This is the layout of the final report. Okay, any questions on this? It's clear? All right. All right, so I also want to show you the LaTeX file just for your information. All right. Okay, so let me share my screen here. So I will upload this zip file. This is a compressed LaTeX sample file. This is going to be uploaded to Blackboard. Now, when you open it, you get this sample. So you have two samples. Each sample has a tech document and also have a BibTeX document, which is the second one here. It also has a class document, which is making sure this is an IEEE format. So these three files will be in you will find it in sample one. Now, if we open the sample here, and this is going to open TechMaker. Let me share TechMaker. This is what you see in the TechMaker. So this is a sample. This is an IEEE transaction. Now you can see here how the layout of the tech file looks like. You have some packages that you are using. So it's under use package. You can see these are different packages that are ready to use. Then you start with a begin document to start your document or article, paper or report in this case. And then you have the title and also the author. This is the affiliation. And then you have the abstract, begin and end abstract, basically start and end abstract. Then you add some keywords for your project. Then you have sections. These sections differentiate between different parts of the paper. Inside the section, you can have a subsection, and you can also add different labels to these sections. So let me run it so you can see what is the output of something like that. Okay, when you run it, you have different types of runs here. One of the called quick build, LaTeX, and so on. There are different types of runs. Usually what I do, I go to configure. Probably this is not visible, so let me change the share. So basically, you will see these choices when you open. So this is came from where? Options, configure, tech, maker, and then you put the quick build. So the one I use usually is this one, which starts with LaTeX, BibTeX, LaTeX, and then DV to PS, PS to PDF, and then view PDF. So if we chose this one and then run this, you will find that it starts a process of compiling the file. And when it compiles, it just use the output. This is the output coming from the compiled file. So you can see the title is here. Then we have the author and affiliation. We have abstract. We have the keywords. We have the introduction, and so on. This is single column, but in your case, you will put it in two columns, which is there is a command also to put things in two columns. And then this is under introduction, which is that section. There's a subsection here, which is related work. Then there's a subsection of contributions. Second section is problem formulation, where you add equations. And if I go back to the files here, you can see how you can write equations. So here's some of the codes to use to write equations. You can get started with writing equations. Another thing to notice here is the references, how references are added. So this is a reference to a section. And you can also refer to a paper. This is a reference to a paper. So when you compile, or let's view the PDF, you can see that the reference to a paper appears here as 1 and 2. And at the very end of the PDF, you can find the references that you are referring to. And then there is also referring to sections. So you can see here referring to section 2, referring to section 3. So there are citation of references, and also there is a reference to sections. And here is how the equations looks like when you are doing these. Now these other sections here, now the 2 question marks here mean that I added a label, but I did not define where the label is in the paper. So these things you need to fix before submitting your final report, or even your progress report. It shouldn't have question marks like this. You can also write lemmas and theorems and proofs for it, and this is how the format looks like. So if you go back to the, you can see here how to write a, first of all, you can write an equation with multiple lines. This is how you like write it, with aligned command. You can also write a lemma and the proof of the lemma. I use the commands for it. And this is the label, which basically you can, when you are referring to this lemma, you need to use the name inside that label. The other thing is also the other thing is also the pseudocodes, which most of you will need for your projects. This is how the pseudocode looks like. So there are some commands that is used in LaTeX to do pseudocode. So you need to define that algorithm. So here is the commands for it. So algorithm is one and algorithmic is another one. So algorithm just writes the caption, and inside algorithmic you just define these steps for the pseudocode. And then there is a simulation section, and there is subsections inside each one of simulations. You end the document at the very end, and before that you usually write you write the file, the location of the file that is used for the references. So how do you enter references? It is from the second file that I just had here. When you compile, you will find that you have a lot of outputs, not just the 3 inputs. Initially, you had only the IEEE transaction and the BUPS, which is a BIP file, and the sample one. But when you compile it, it gives you all these outputs, including a PDF file, which has the output you need. And now the BUPS one, if we open this one, this is actually the one that has the references. So this is how you add the references in your LaTeX. So add article and then write the article, some symbol here, or add some name for that article, and then you add the information about the article, the author, the title, the journal it's used for, date, and so on, these type of information. You can find some of these online already ready. For example, IEEE usually have a link that gives you directly the LaTeX format of the reference, or you can enter it. Like, for example, these are just something I entered. And there are different article, or there is proceeding if it's a conference, article if it's a journal. So you can also link to a website, and you can also do other as well. So try to look into different types of references and how you can write them. Each one of them has different also inputs here. Yeah. Right. So the last thing that is remaining is the figures. So I left this for sample 2. This is sample 1 that doesn't have the figures included. Now, if you open sample 2, you will find that sample 2 has additional 3 additional files, and all of them is .eps, and this is one of the formats for the images that is used by LaTeX, but there are other formats as well, so you can look in different formats. So if we open sample 2, and we do a quick build similar to the one we did before. So it's the same it's the same report or the same sample, but here it's a double column. So your submissions should be in a two column like this one. And at the same time, it has figures. So you can also see how figures can be added to a paper. Now this one also is more complex because it has one figure and three sub-figures. So this is figure 1, and then there is figure 1A and figure 1B and figure 1C. So now you can see how you can add different figures inside sub-figures inside just one figure. So it's one thing also to consider here. So the command for it you can find in the sample. So here is the command. Command is begin figure, and then you can add sub-figures, or you can just have one figure, and figure 1 can just have one figure, don't have to have many. But you can see here each one how it is labeled and how it is included. So you say include graphics, and then you add the figure file name and just run it. So just test these type of samples so you can get familiar with how to use LaTeX. Okay, any questions? Good. All right, so that's for the project. Now you also have the deadlines for each submission is already uploaded. The first deadline you have is going to be February 27th for the project proposal and the quad chart. But before that, in February 23rd, you will have your presentation, which I'm going to send this weekend. I'm going to send an announcement who is going to present when, and just also trying to adjust for the for students that are online. Okay. So now let's go back to our notes. Where did we stop last time? So we had the general examples that we're going to use through this lecture. One-time bad, variable length, one-time bad, additive one-time bad substitution. All these we are going to repeat for different cases. Last thing we talked about is about perfect security. Let me share my screen here. Last thing we talked about is perfect security. Mario, can you see the notes? I can't hear you. Let's see if I'm muted or not.
Sorry, yes, I can see them.
Okay, thank you. So last thing we talked about was perfect security, and we said perfect security is basically if you have a Shannon cipher divided over KM and C, then consider a probabilistic experiment in which the random variable k is uniformly distributed over k if for all m node in M1 belong to M and all C belong to C. We have the probability of encryption of message M node and message M1 are equal. So you encrypt message node and get an encrypted text, cipher text, which is C. It's basically not going to be distinguishable from if you encrypted M1 and get the message another one C. Then we say this is a perfect secure channel cipher. We did prove that these are equivalent. If the cipher is perfectly secure, that means that for every C in C, there exists an integer in C such that for all M belong to M, we have that the number of keys that can encrypt and get the same cipher text are equal. We have equal outputs. now if a random variable k is uniformly distributed over k, then each of the random variable e of km for all m belong has the same distribution. Now, if I have set of keys that are uniformly distributed, which should be the case because you shouldn't prefer one key over the other, and you do use it to encrypt any message m, then the distribution of the outputs has to be the same for all messages. This way you cannot differentiate between them. And then we looked into the proof of this. And we took an example of what is a uniform distribution and what is not uniform, non-uniform distribution. Uniform distribution, if you have, let's say, 5 elements, then each one has a probability of 1/5. A similar case of uniform distribution could be a fair dice, where you have 6 faces. Each one has 1/6 probability. So this we consider uniform. If you have also a fair coin, so have 2 faces, each one have 50% because they are uniform. So these are all type of uniform distributions. Then we showed that the one-time bad is perfectly secure because it satisfies that you cannot tell from the output what is the message that was being encrypted. Even get any type of information about that. And this is a special case where the number of keys in C is equal to 1. It doesn't have to be the case. And then we looked into variable length one-time bad. And we said it does not satisfy the perfect security since ciphertext has the same length as the corresponding plain text, which basically means that it gives you information about which message was being encrypted. So if we only have 2 messages, one of length 1 and one of length 2, then the ciphertext of length 1 means that basically the probability that the message is M1 is equal to 0, cannot be M1. We look in substitution cipher, which also we said it's not perfectly secure, and we said this is not perfectly secure because some of the messages, some of the letters in the message will be more frequent than other, which basically if you have enough inputs from that sequence of encrypted messages, you can tell that this message is more likely if, for example, you have a specific letter that is the most repeated letter, probably it was originally the letter E. This way you can tell that this cipher text or the letter that is the encrypted letter is basically originally E. So this gives you advantage in knowing about the message. And then we looked into additive one-time bad, and we said that this is perfectly secure, again, by using the second part of the theorem. I think this is where we stopped last time. We talked about if we have a cipher, Shannon cipher over Km and C, consider a probabilistic experiment in which K, okay. Now we try to look into something else, which is called the predicate. So a predicate is basically a type of a function that you use to try to find some information about the encryption. And we will have a lot of examples of different predicates. One of them, for example, being the parity. So if you can, using the parity of the ciphertext, get some information of the original message, then this is a problem. So the predicate is basically a function that you apply to the encrypted message and gives you some information. If it does not give you anything, then this is secure. So E is perfectly secure if and only if the predicate M node and M1 belong to M, they are exactly equal. If they are exactly equal, then we say that it is perfectly secure. And then we had a proof for that. Okay, so this is the last part we stopped. Maybe I can just give you a reminder what was the proof about. So E is perfectly secure. Let phi M node and M1 be given, and let S C in C and phi in C. For C and C, we have phi in C. Then we have probability that phi of E of K and M node is equal to the summation of C in S, probability of E of K and M node equal to C. This is a common way of doing proofs in probability. where basically you add the realization and sum over all realizations. So when you say this is equal to C, then you give it a value. But C summed over all values, so this actually sum up to the probability itself. This is a way of doing this. And then because it's perfectly secure, you can substitute the probability instead of M node to M1. So you can change the message because they are equal, they are perfectly secure. So the assumption that it is perfectly secure, so it has to satisfy this one. Okay. Because it satisfies this one, then you can do this substitution. And then basically this is the same as this. So basically this means that they are equal. Okay. So now the converse is suppose E is not perfectly secure. So there exists M node and M node, M1 and C such that these are not equal. Then the probability of the predicate, which is basically equal to probability when you submit the realization C, does not equal to the probability for M1. And this means that it's not equal to the probability of the predicate. And there is where we stopped last time. Let's continue. I have another theorem here, which is also useful to go over the proof of it. So one of the things about these proofs is that when we go into looking into other type of encryption and try to look if this is doable or this is secure or not, we'll have to work with some of these steps that we are using in the proofs. So even though this is kind of theoretical, but eventually when you have examples, we'll take some examples later about some attack games. When we look into some attacks and try to figure out if these attacks we can work or not, we will actually need to use some of these techniques we're currently using in these proofs. So it's important to learn about these early on. So here's another theorem. So let's say also we still have the cipher E and D. E Shannon. Cipher. Defined over A M C, which is again the sets of the keys, the message, and the cipher. Now consider a random experiment in which K, random variable K, and M, random variable M, these are random variables such that first K is uniformly distributed over K over K. This is the set K, and M is distributed over M, and K and M are independent. define a random variable C by definition is equal to E K M. So this is a random variable, and this, so again I use the bar under the variable to refer to random variables. Then we have if E is perfectly secure, then C and M are independent. Okay. And the converse, so conversely, if C and M are independent, and each message in M occurs with non-zero probability, then E is perfectly secure. Okay. So first, before going into the proof of this, we first need to know what does the notion of independence mean. So when I say first is the same definition, we have the same Shannon cipher over K, M, and C. Num K is uniformly distributed. We now know what is the uniform distributed random variable, like, right? M is distributed, so M is not uniformly distributed. So why M is not uniformly distributed?
Messages can have like any sort of normal distribution.
Yeah, because the message is basically gonna,
Arbitrary.
yeah, the message is gonna be a set of words. This word doesn't have to be equal, like you don't have equal probability of all letters inside the text, right? So it doesn't make sense to make M uniform distributed. So this is why the assumption that M is distributed is okay, but it's not uniformly distributed. And also we assuming there is non-zero probability. So basically you're gonna use all the letters when you're writing a message. Now K is uniformly distributed makes sense, right? Because if you are picking a key, you are deliberately picking a specific key at random. So you want to have equal probability of picking any key from that set. Now, the other thing that is in the design is that the key and the message are independent, which is also makes sense. If you have a specific message, you don't want to pick a specific key for that specific message, right? No, if you are sending the same message 10 times, each time you need to pick a different key. There is no correlation between the key and the message. The key is picked at random. That's why they are two independent random variables. So is this clear about the independence here? Meaning that even if you are sending the same message, every time you pick a random key for that specific message. So there is no dependence between them, and then they are independent random variables. Now we are going to define, now we have the key, we have the message, we are going to define our encryption as always. It's basically equal to the encryption of the key and message, which is also a random variable. Since there are two random variables inside the function, so the output is going to also be random. I don't know, because the input is not deterministic, the output is not deterministic. So if E is perfectly secure, then here is the result. If the E or the cipher is secure, then I should also get that the ciphertext is independent of the message, which is what we want, right? We want a final ciphertext totally be different from the, or is not related to the plain text. This way we make sure that they are, that we have a secure system. Which is also can be proven the other way around. So if you can show that the message and the ciphertext are independent, like you can find a way that this scheme or this cipher technique isn't showing its independence, then you can say that it's also perfectly secure. All right. So let's start with the first part, which is basically assume that E is perfectly secure. Okay. So consider any M in M and C in C. So any message inside the message set and any cipher inside the cipher set. So what we want to show that we want to show independence. So how do we write independence in probability? The probability of C equal to C, and this is the ending, M equal to M is equal to probability of C equal to C times probability of M equal to M. So this is just a definition of independence. If you have two random variables and you do the intersection between them, or you do the ending between them, basically if the ending ends up in product, this means that these two random variables are independent. So this is the definition of independence of any two random variables. So this is not something new. So this is what we want to show. So what we have is the following. We have, so you're gonna start with the left-hand side. So the probability that C is equal to C and M is equal to M is equal to probability that, what is the C, random variable C? It's E of K and M equal to C, and M is equal to M. Correct? So I can just substitute. I know that C is equal to E of Km. So I just removed that equation and replaced it with E of K and M. What else can I do in this step, after this step? So in the first event, I have two events here. I think these two are happening at the same time, which means the second one is also happening as the first one is happening. Okay, if the second one is telling me that the random variable M is equal to M, it has a realization of M, which means that if these two are happening at the same time, then the first term has to have the random variable equal to M. Correct? So this is equal to probability of E of K and M. Correct? Equal to C, and M is equal to M. Yeah. C is equal to M. M is equal to M. So basically, because already there is a realization and I'm finding the common event, these two are happening, which means the second one is happening. So since the second one is happening, it's gonna affect the first one by that substitution. Okay, what else can I do? Now the first term only have the random variable k, and the second term only have the random variable m. Then what can I do about that? The whole function in the first term only have one random variable, which is k. The second function or the second event, in this case, only has a random variable, which is m. And what do I know about k and m? Independent. It's given, right? I choose a key to be independent on the message. I want to show that the message is independent on the cipher. But I know that initially I'm choosing the key totally independent from the message. So now if I have two events, one event has only the key as a random variable, and the second one has only the m as a random variable, then this can be two independent events, correct? So this is equal to probability E of k m equals c multiplied by probability of m equal m. This is from independence. From so I'm gonna write independence as a perpendicular just for short. So this is independent. All right, so far. So to show, so what is missing here? What is the remaining part? I want to show again. I remember I want to show this. Right? So it starts with the left-hand side. In the right-hand side, I need to have m, probability of m equal to m multiplied by probability of c equal to c. If you look down here, I already have this part already done. This part is done. So this part is still not done.
C bar, then will be the last portion of the first term, E of parenthesis K bar, comma M replaced with C bar, right? Just the encrypted message.
But the definition is saying that c is equal to e of k.
Oh, the both.
So, but it's something close to what you said. So now I want to try to basically equate this part with this part. This part, I want it to be equal to this part. So I will do that. So I'm going to start with probability of c equal to c is equal to probability of e of k m equal to c. Now this is equal to probability of e, k, and m equal to c and m equal to m. So when are these going to be equal? If you sum over all values of m in the set. Okay? So I added a random variable and give it a realization, but then I added the whole set. So these are two equal probabilities. This is also one of the things that people use a lot in proof for probability. So if you have only one random variable, but you want to add another random variable in the equation, you can end with it, but you need to sum all realization for that random variable, which is what we did here. So we summed over all realization of M. So, and we ending it with it. Basically, it cancel it out because it's gonna sum all of it, so it's gonna be 1, and then the remaining probability is only gonna be the probability of the encryption. And then this is equal to sum oh, there's a line here, don't know why didn't work. Okay. So the same thing, if I'm ending with a realization, I can just substitute with it because I'm saying that these two events happened. Okay, this is equal to. Now these are also two independent events, right? Similar. Right, same idea by independence. Now this is equal to. So how did I get to the last one?
When we did the predicates, you did a similar thing.
I did, and then the end.
When we did the predicates, I think you did a similar thing
Yeah,
with the last one.
yeah. So basically, the second term is the same. The first term will change it from M prime to M. So why these are equal? Because we are assuming perfect security. Perfect security. So again, what are we trying to prove? If E is perfectly secure, then C and M are independent. So because they are perfectly secure, if you use a random key to encrypt a message M and use a random key to encrypt a message M prime, it should be give you the same cipher with equal probability, right? Which is basically this equation is saying. If you encrypt with a random key M prime and encrypt with a random key M, they're both going to give you the same cipher. So this comes from perfect security. Just let me add this note. This is from perfect security. And this one comes from independence, A and M. And this one comes from what is known as the total probability. Basically, one of the characteristics of the probability that you can add and sum over all the values. All right, so now M is different from M prime. So I can take this outside the summation. And then the summation is only going to be over. What is the summation? 1. So this sums up to 1 because you are summing all the values of M. So this is probability sums up to 1. So eventually this is equal to probability of E of K and M equal to C. And again, this goes up to 1. Which means that I was able to show that this side is equal to this side. Right? So now this is proves it. All right. All right. Now, so this is the proof of it. Now for the second part. So assume that C and M. Remember the second part, we start by the assumption that C and M are independent, and then we want to say that this is perfectly secure, the other way around. So are independent. And each message in M occurs with non-zero probability. So all the messages are going to be used in the transmission. And then let M is in M and C in C. Now what we want to show is we want to show that the probability of E of K and M equals C is equal to the probability of C is equal to C. From which perfect security follows. Yeah. So basically, if I was able to prove that second part is equal, that means that inside this proof, it means that somewhere it's perfectly secure, otherwise it wouldn't be equal. So if I can show that they are equal, then I can show that they are perfectly secure. Okay, given. So now I have information that we have non-zero probability. So given that's the probability of M equal M is non-zero. We said that there is no message that have zero probability. Then it's called probability of E of K and M equal to C multiplied by the probability M equal to M is equal to probability E of K M equal to C and M equal to M. Okay, so why is this true?
And we're starting with the point that they are independent as well.
Yeah, this is true because K is independent from M. Okay, so the intersection will be equal to the product. Okay, this is equal to probability E K M equal to C intersection with M equal to M, which is basically equal to probability of C is equal to C intersection M is equal to M. Now, given that we have C and M independent, this is equal to the probability C is equal to C multiplied by the probability M is equal to M. That's because C is independent from M. And at the same time, we can cancel these two sides, M, probability of M equal to M, because it's non-zero. So we can cancel them, which means that we can prove that these are equal, which means that we have the other side of the proof already done. All right. So that's all for the perfect security. Because both of them are independent, and since I have a realization of M, then I can add the independent one in the first term. Right. So one of the issues that we have with the perfect security is that, as we saw in the one-time bad, is basically if you need to do an encryption of a message of length L, you need to have a key also of length L. So that makes perfect security difficult to achieve in practical situations. This is one of the things. So we have been talking about perfect security and defining it, which is good. But in practical encryption methods, we cannot use it because, for example, to encrypt a 1 GB size of a file, you need 1 GB key to encrypt it. And now to be able to communicate the key with the receiver, then you also need some type of a secure way of sending the key to the receiver. So it becomes also a burden to send the whole key to the receiver side, which is basically if you're going to send the key anyways, you can just have send a message. So it becomes impractical to use a perfect security to encrypt because you need a very long key. So there is a proof for it, but I'm just gonna skip this part. And the main thing I want to
Packets, let's say you're saying we have 1 GB of methods.
yeah.
So can you have a smaller key, let's say 1 megabyte of key, and like take each megabyte and encrypt it, just like packets. So that way we will not have a lot. I mean, we will have we'll use 1 megabyte of key to encode every 1 megabyte of.
But it's going to be the same key. Is it the same key?
We can have the receiver set, let's say we will have, I mean, the receiver also have to have the knowledge of what should be the key, right? The receiver.
And this is the thing, if you are gonna have, yeah, so if you're gonna select, let's say you have a 1 gigabyte, you can just encrypt the whole thing with one key, so it's gonna be a very long key. Or you can divide it into smaller chunks and have the same key for every part. But it's not gonna be perfectly secure because it's the same key, right? But if you choose a random key every time, then you are basically also sending all these keys every time. So basically, you either send the multiple keys for each one, or you send one big key. So either way, you have to communicate the key itself. So if you're communicating the key, you already can communicate the message, because anyway, if you have a communication between the transmitter and the receivers, you can just do that. And also becomes a, let's say, even if you want to store a 1 gigabyte and you want to have a 1 gigabyte key for every 1 gigabyte you're going to store, so it's just going to be not practical to use. So that's why perfect security is not, it's perfect, so it's not really practical to use. But we have something that's very close to it, which we are going to discuss maybe next time. So I just want to add this note. There is also a proof for it, but there is no need to go into the proof for this one. I'm just going to mention that so for perfect security, keys must be at least as long as a message. Hence, yes. Anyway, okay, I'm gonna write it next time. So the main idea is that we need to find more practical techniques that we can use, and we'll also have a sense of security that we can implement as well. All right, thank you, and see you next time.